an almost closed form for Hardy's integral featuring hypergeometric function. The integral is integral from 0 to pi over 2 of dx by a cos square x plus b sin square x to the power n, right? And I actually got this integral from Maths 505, and his solution was in terms of infinite series. And then I thought of, why don't I try to find a closed form? And then in that process, I actually got the solution in terms of hypergeometric function, and here I present it. Actually, it's really beneficial because this is the general solution, and we can use that hypergeometric function to solve it for any n. And yeah, I think it's pretty nice. Regarding Hardy, I want to say a thing. I have actually read a beautiful piece by Hardy called Mathematician's Apology. This is the article, and this is so good. Like, was something about why maths is an art, something like that. I will attach it in description, and I hope you wanna have a read it. I wanna read that. So let's try to solve this. 0 to pi over 2 dx by a cos square x plus b sin square x to the power n, right? So my first try will be to reduce number of trig variables from 2 to 1. So for that, what I will do is use the Pythagorean identity and write this as 1 minus sin square x plus b sin square x to the power n. And now this becomes integral from 0 to pi over 2 dx by a plus b minus a sin square x to the power n, right? And then I want to try to change this from trig integral to some algebraic integral. So I'll make substitution t is equals to tan t. This actually works pretty well. Sorry, t equals to tan x, and that actually works pretty well. Let's see. So with this, x is tan inverse t, and then dx is 1 by 1 plus t squared dt, right? And not just this, also sin squared t x will be tan square x by sec square x. And since sec square x is just 1 plus tan square x, this actually becomes t square by 1 plus t square. So now integral will go from 0 to infinity, right? And 1 by, this is a plus b minus a sin square x is t square by 1 plus t square. And then to the power n, dx is just 1 by 1 plus t square dt. So now this integral becomes integral from 0 to infinity. Now this goes to numerator. And also there's this factor that divides it. So 1 plus t squared to the power n minus 1. And in denominator, we will have a times 1 plus t square plus b minus a times t square to the power n dt. So now this again simplifies to integral from 0 to infinity. 1 plus t squared to the power n minus 1. And this becomes a plus at square minus at square is 0. So bt square to the power n dt. To simplify it further, let me take the a common. So 1 by a to the power n integral from 0 to infinity 1 plus t square to the power n minus 1 by 1 plus b by a t square to the power n dt. Now let me make a substitution to simplify it even further. The substitution is x equals to t square. That gives me t equals to x to the power half, and dt is equals to half x to the power negative half dx, right? And that gives me 1 by a to the power n integral from 0 to infinity again, right? 1 plus x to the power n minus 1 by, and 1 plus b by a x to the power n, and then dt is half x to the power minus half dx. So that gives me 1 by 2a to the power n integral from 0 to infinity x to the power negative half 1 plus x to the power n minus 1, and then 1 plus b by ax to the power n. Negative n. And this reminds me of a similar kind of integral known as the hypergeometric function. So the integral related to hypergeometric function is this. The integral from 0 to 1 of t to the power b minus 1, and then 1 minus t to the power c minus b minus 1, and then 1 minus tz to the power minus a dt. This is actually equals to hypergeometric function. This is actually simple hypergeometric function of a, b, c, g with along with the product of gamma of b, gamma of c minus b by gamma of c. So this is the thing that we're gonna use this integral. And also, if you do not know about hypergeometric function, simple hypergeometric function, I will just give the definition, and that should be enough for now. Definition of this is just sum from k equals to 0 to infinity of a sub k, b sub k by c sub k, and then g to the power k by k factorial, where this a sub k is defined is the rising factorial, which is defined as a plus 1 up to a plus k minus n in this way, right? And notice that this doesn't really define for k equals to 0, and so for 0 we just define it to be 1, just like the factorial. Yeah. So yeah, this is the thing, and we are gonna use this. And let me just try to write a different form of this integral. I mean, if it's in, let's say, this form, t to the power p 1 minus t to the power q 1 minus tz to the power r dt. So what if it's in this form? Then first of all, now notice that now a is negative r, right? And then our b is actually p plus 1 now, and then our c is actually q plus b plus 1, so p plus q plus 2, and our z is still z. So yeah, and now gamma of now b is b plus 1, gamma of c minus b is q plus 1 by gamma of c is b plus q plus 2. So yeah, this will be the answer for this integral. So now the only thing that we want to do is to transform this integral into this integral, so that we can now use this thing formula, right? And for that, we need to make two changes. First of all, transform this positive sign to negative sign as given here. And also, limits of integral should be from 0 to 1, right? So let's see how we can do that. We can actually do both the things at the same time. So let's see how. So now we know that this is 1 by 2a to the power n integral from 0 to infinity x to the power minus half 1 plus x to the power n minus 1 1 plus b by a x to the power minus n dx. What we can do is we can make a substitution that does the both job, to introduce negative sign as well as make this limit go from 0 to 1. In that substitution that works is we can actually make a substitution that is t is equals to 1 by 1 plus x. Because if I make this, first of all, notice that limit now goes from 1 to 0, right? In 1 to 0, we can just reflect it to make it 0 to 1. That's not a big deal, right? Also notice that in this case, 1 plus x will be 1 by t. So x will be 1 by t minus 1. And then and then x will be 1 minus t by t. So we notice that over here in place of x, we will have 1 minus t, right? That's a good thing. Also, here, if you have 1 minus t, that just cancels. Here also, we'll actually have pretty good results. Let's see. And also notice that dx actually becomes negative 1 by t squared dt from here. See? Okay, let's do it now. So this becomes 1 by 2a to the power n integral from 0 to infinity, right? Let me do it a bit over here just to save some space. Okay, and then we will have this as 1 minus t to the power negative half by t to the power negative half, and then 1 plus, and that's just 1 by t minus 1 to the power n minus 1, and then I think I need to move this a little bit. I think I just messed it up. Let me take it. Let me take it down because I don't think they have enough space over there. Okay, and then 1 plus b by a, x is just um 1 minus t by t, right? Minus n, and dx is negative 1 by t squared dt. I forgot it's in the limits of integral. I'm sorry. Limits of integral is from 1 to 0, right? Is that all good? 1 minus t by t, and then 1 minus minus 1, 1 minus t by t. Yeah, that's all good. Now you can use the negative sign to reflect the limits of integral, as I said earlier. Becomes 0 to 1, and then 1 minus t to the power negative half by t to the power negative half. This just becomes 1 by t to the power n minus 1, and this actually becomes at plus b1 minus t to the power minus n by a to the power minus n, t to the power minus n, and then 1 by t squared dt, right? Negative sign is already used to reflect the integral. Now notice that a to the power minus 1 actually cancels with a to the power n, so we have 1 by 2 integral from 0 to 1. Also notice that t to the power minus n and t to the power n just cancel each other out. So we have t to the power minus half, right? And t to the power minus 1 with t squared. So that's just t to the power half in denominator, or t to the power minus half in numerator, right? And then we have 1 minus t to the power minus half as well. And then over here, what do we have here? B plus a minus b t to the power minus n, right? Notice that I can actually take b common from there. So if I do that, I will have 1 by 2 b to the power n, right? Because there's negative power. And also notice that in my standard form of hypergeometric function, I actually need a negative sign over here, right? So I will make 1 minus b minus a by b t to the power minus n dt. I did this because I need negative sign over here, right? Okay, so now that this has been reduced to the standard hypergeometric function integral, now let's try to use that. So if we use that, we will have 1 by 2b to the power n, and this is reduced to the hypergeometric function of first of all negative r, right? So just n, and then p plus 1, right? So just half because p is negative half, and then p plus q plus 2, right? Q is negative half, p is negative half, so negative 1 plus 2, which is 1, and then g is b minus a over b. And for other, this is gamma of negative half plus 1 is the gamma of half, gamma of again half, and half plus half, that's just 1. And yeah, we got the general answer, guys. Moment of happiness, no? Okay, now gamma of half is root pi, so root pi times root pi is pi. So pi by 2 b to the power n, and then 2f1 and half 1 b minus a by b. Yeah, we got the general answer, and I'm so excited. So I'm excited to try this function, this answer, and then get different answers, right? So yeah, to verify this and also mix to just see how powerful this is. So yeah, let's do a couple of examples. So first of all, let's try to find this integral now. 0 to pi over 2, 1 by a cos square x plus b sine square x to the power n when a is equals to b. We know that if a equals to b, this just becomes integral from 0 to pi over 2 and 1 by a to the power n, right? And that's just pi by 2a to the power n. Let's see if that's true. Yeah. So if a equals to b, I can actually write this as pi by 2a to the power n, right? For a equals to b, I can write the answer as, and then pi by 2a to the power n, and 2f1, this becomes n half 1, and b minus a becomes 0, right? So we have this. Now we know that our hypergeometric function is defined as, for a, b, c, g is defined as sum from k equals to 0 to infinity of a sub n, b sub n by c sub n, g to the power n by n factorial, right? Yeah, sorry. I should have said k, not n, right? That's the sum, right? Okay, so now that becomes a sub k, b sub k by c sub k, g to the power k by k factorial, right? Now, notice that if you want to find 2f sub 1 of n half 1 0, that will just be sum from k equals to 0 to infinity. Now that's n sub k, half sub k, 1 sub k, and then 0 to the power k by k factorial. You might tell that this is always 0, right? So that's just 0, and then our answer was supposed to be this though, but that's not the case, because when k is 0, 0 to the power 0 is 1, right? At least in the limit it's 1, right? So if we use that, uh, first term will survive. All of them will just go to 0, except for k equals to 1, 2, 3, and so on. But for k equals to 0, 0 to the power 0 is 1, so that gives us n sub 0, half sub 0, 1 sub 0, and then this 1 by 0 factorial. And then we know that all of these sub 0 are 1. I already told that earlier, right? These all are just 1. So that's why we have 1. Wait a second. Okay, yeah. Yeah, okay. So 1, 1, 1, 1, right? So that's just 1, right? So we see that this is actually just 1. So that's why this actually becomes pi by 2a to the power n times 1, which is pi by 2a to the power n. So our this general formula actually gives us answer as pi by 2a to the power n, right? Which is exactly what the answer is. Now let's try to solve for one more answer. So when okay again, let's try to use this general formula to solve for the case of n equals to 1. Okay. So first of all, we just know the answer by ourselves, that let's say uh if this is the case, if n is 1, so for this one we can actually easily solve it if we just multiply numerator and denominator by sec square x, because that gives us a plus b tan square x. Now if I make a substitution that t is equals to tan x, I get 0 to infinity dt by a plus bt square, and that gives me 1 by root a tan inverse root bt by root a with 1 by root b from 0 to infinity, and this is 1 by root ab pi by 2 minus 0. So I get pi by 2 root ab, right? So I can also verify this answer using my general answer, right? Which was, what was the general answer? Pi by 2b to the power n, pi by 2b to the power n, 2f1, and then n half 1 b minus a by b, right? So let's see how this can actually give me the general answer. Now in this case, our n is 1, right? So in this case, the answer should be pi by 2b, 2f1, 1 half 1 b minus a by b, right? So let's see. Now this becomes pi by 2b, and this is a sum from k equals to 0 to infinity, 1 sub k, half sub k, and I actually gave the definition, right? Uh, yeah, okay, you have the definition, we'll use this. So this is half sub k, 1 sub k, and then b minus a by b sub k, right? And this becomes pi over 2b. This cancels out, right? So we have sum from k equals to 0 to infinity. Now I can write this as half plus 1 up to half plus k minus 1, right? And also I forgot something. Also we have k factorial over here, right? As you might see over here, k factorial. So yeah, this all this thing half plus k minus 1 by k factorial, and then 1 minus a by b to the power k, right? And now that also reduces as pi by 2b. Now I can write this thing, the numerator, as 1, 3, 5 up to, notice that the last term is 2k minus 1 by k factorial, and then 2 to the power n over here, because, sorry, 2 to the power k over here, because there are k terms over here, right? And with 1 minus a by b to the power k, right? This becomes pi over 2b. So now again, I can actually write this as, I can make numerator as 2k factorial and introduced 2 to the power k times k factorial in denominator. You can see how that works if you just try to expand these things. And then we already have k factorial times 2 to the power k, right? 1 minus a by b to the power k. Now I can write this as pi over 2b, sum from k equals to 0 to infinity. This is 2k factorial by k factorial, and then now this becomes 1 over 4 minus a over b 4b to the power k, because I'm just taking this 1 by 4 to the power k inside this expression. Now I have pi over 2b, sum from k equals to 0 to infinity, 2k over k, and then 1 over 4 minus a by 4b to the power k. Now it can actually be proven using binomial expansion, or also I have proved in one of my videos that this function has a really good binomial expansion, right? Which is just the central binomial coefficient times x to the power k. So if we use this fact, notice that this actually x actually has to have the modulus of less than 1 in this case, and we just assume that. So if you do that, we have pi over 2b. Now this will this expression now can be written as 1 by square root of 1 minus 4 times x is 1 by 4 minus a by 4b, right? And that gives us pi over 2b, 1 by square root of 1 minus 1 plus a by b. And beautifully, I think you see where it's going, square root b by a. So that means pi by 2 square root ab. And that actually verifies that the answer is correct, because that's what we were supposed to get, right? And even our general solution gave the same answer, pi by 2 root ab. So this is so beautiful, right? And not just the solution, the fact that how we could actually go from hypergeometric function to our actual answers by using this generating function. This is pretty cool, guys. Maths is so interconnected and always true, bro. So yeah, so we did verify that our answer is correct by two different simple cases. And the fact that there's such a general answer using hypergeometric function is also pretty cool, no? Bro, who knew maths was so beautiful? And just summarize the solution. We first reduce this to algebraic problem and notice that this actually seems similar to the integral of hypergeometric function. Then, but the limits and the sign were different. We tried a substitution to take it to the required form, and then used hypergeometric function, and then verified it with two specific answers. That was it, guys. Hope you enjoyed the video. Thanks for watching, and yeah, do share with your friends if you like it, and I love to see it in the next video. Love to see you in the next video too.